All right, in this lecture, what I'm going to do is I'm going to take you through two of the more important concepts in environmental economics. As you've no doubt picked up upon, a big part of this course is our conversation about the cost effectiveness of environmental policy. What this means is that in environmental economics, often our goal is to establish an optimal amount of pollution reduction, what we call abatement, not only what the optimal abatement level would be for an entire industry, but as you'll see in this lecture, we also can extend that to now show what would be the optimal abatement level per firm. So we can establish what the optimal abatement level is for an industry, and then we can also establish what the optimal abatement level would actually be for each firm in that industry. Okay, so what we'll do to show this is to take you through a very straightforward example. And in this example, what I want you to imagine is that there's a river, and the river is being used to ship goods down it. And as a result, there is river pollution. So we have total damage, which comes from polluting the river, and then we have total benefit, which this is from the firm's perspective, or the firm's, multiple firms' perspective, which is the economic benefit of polluting the river. This is, of course, one of the controversial distinctions that sometimes occurs in environmental economics, where we consider pollution as a form of economic benefit. Sometimes students have a problem with this because their argument would be that we should always frame pollution as inherently a negative. And that, I think, to a certain extent is true. However, in this particular scenario, what we're envisioning is an abatement plan, an abatement strategy, which recognizes both the damage of the pollution caused by the economic output, but also the social benefit of the economic output. So here we have two functions. We have a total damage function and a total benefit function. We can see that both functions are themselves made up only of river miles, and this is river miles polluted. So the total damage basically is equal to the square of the river miles polluted, and the total benefit is equal to this particular function. Just notice that the only thing that shows up in this function is polluted river miles. It can be a little confusing sometimes, but just, again, keep in mind, these are polluted river miles. So what we can do is we can take those functions, those total damage and total benefit functions, and we can find marginal damage and marginal benefit functions from those. Mathematically, we would do this by taking the derivatives of those functions. In this course, 300 level economics course, I'm not going to ever have you need to take a derivative. If there's ever anything that involves a derivative, I will take the derivative for you. But I do want you to see, those that have a little bit of a calculus background, and even those who do not, that the way that we derive marginality is always by taking derivatives. So the marginal damage function is simply the first derivative of the total damage function, and the marginal benefit function is simply the first derivative of the total benefit function. And again, if these words don't mean anything to you, it's probably not a very big deal. But those of you who've had a calculus background, this should seem very straightforward. If you don't have a calculus background, ignore this whole conversation about taking derivatives, and just focus on these functions themselves. So when I say these functions, I mean the marginal damage and marginal benefit function. So what is marginal damage and marginal benefit? Well, these functions refer to the additional damage, in the case of marginal damage, that occurs when additional river miles are polluted. So every river mile that is polluted is going to have a marginal increase in damage calculated by the marginal damage function. On the same token, we have the marginal benefit function, which tells us the economic benefit that changes every time we add an additional polluted river mile. And so again, what we're interested in here is this notion of thinking on the margin. If you think back to your 106, your economic principles course, you'll remember that one of the ways to quote-unquote think like an economist is to think on the margin. And so what we're doing here is we're generating marginal damage and marginal benefit functions so we can do exactly that. We're going to solve this problem by thinking on the margin. To do so, what we'll rely upon to establish the optimal amount of pollution, or to put it another way, the optimal amount of pollution reduction, we will use the first equimarginal principle. The first equimarginal principle tells us that total net benefits, that is, total benefits minus total costs, will be maximized when marginal benefit equals marginal damage. What I mean by this is that if our goal is to maximize the net benefits of society, then the way in which we will go about doing so is finding the amount of polluted river that equates marginal benefit with marginal damage. Okay, so here we can see this in the graph, and let me take you through this graph and sort of suggest to you that this is a fairly straightforward point. You'll notice in this graph that we have a marginal benefit function and we have our marginal damage function. You'll notice that for polluted river miles below M star, and again remember, M here refers to polluted river miles. So if we restrict pollution to below M star, we should notice that the marginal benefit, which comes from the economic output of polluting the river, is higher than the marginal damage being created by that pollution. This would mean that at low levels of river pollution, it's in fact beneficial for society to increase allowable pollution and to get us closer to M star. So because marginal benefit, again, this is social marginal benefit, is greater than the social marginal damage, then we want to continue to allow pollution in the river. We want, so imagine there's currently 5 units of pollution, somewhere around here, meaning that marginal benefit from that pollution level is much higher than marginal damage. This means that if we allow additional pollution, we will achieve higher total net benefit. On the other hand, beyond M star, we can see that marginal damage is now greater than marginal benefit, implying that it's not worth it from a social perspective for us to allow more than M star level of pollution. That beyond M star level of pollution, society now suffers marginal damage at a greater amount than it benefits here in the context of marginal benefit. What this means is that according to the first equimarginal principle, the socially efficient pollution level will be M star. If you'll recall from the initial setup of this question, the total river miles were 50. So the 50 is the total length of the river, and that currently 50 miles were being polluted. Well, if we look at this graph, we can see here at M50, this is way beyond M star, right? An M of 50, which is the current pollution level, is way beyond M star, and we're certainly creating much more marginal damage than we are receiving in marginal benefit. So clearly 50 river miles polluted is not socially optimal. So our goal is to establish what M star is, and then that way we have a strategy of how much pollution we should reduce, otherwise called abated. How much pollution should we abate from the river, and how much pollution should we abate from the river, and do so in an optimal way, in a cost-effective way, meaning that we want to abate pollution such that pollution that is left is M star. We don't want less than M star pollution. We don't want greater than M star pollution. M star pollution is the optimal amount of pollution relative to social welfare in this particular example. Now, again, this can seem a little controversial, especially to the more environmentally conscious among us, to suggest that there is any good amount of pollution. But again, remember, in environmental economics, we're attempting to weigh the economic benefit of here polluted river miles with the social damage caused by the pollution. And in a sense, we want to kind of bring those two factors into equilibrium, and that's what the first equimarginal principle does. It establishes for us the optimal level of pollution for a given circumstance. And here we just have some general rules to make understanding the graph a little bit easier. For any pollution less than M star, again, we established that marginal benefit was greater than marginal damage, meaning that we should increase pollution. And for any M greater than M star, we saw that marginal damage was greater than marginal benefit, so we should reduce pollution. Okay, so we can do the math now. So again, we want to set marginal benefit equal to marginal damage. And again, I got these functions from the actual marginal damage and marginal benefit functions. So when we do this math, when we set marginal benefit equal to marginal damage and solve for M, we should see that the socially efficient level of pollution is 25 units. This means that any pollution greater than 25 does not maximize social welfare, and any pollution level below 25 also doesn't maximize social welfare. Given that the optimal amount of miles is 25 and that the current pollution level is 50, this would imply that the socially efficient pollution reduction is therefore 25 units. So now we have a pollution strategy. We want to reduce river mile pollution by 25 miles and allow the other 25 miles to continue to stay polluted. We can see this if we compute net benefits, which is total benefits minus total damage, at these various pollution levels. You should see that as we approach 25 polluted river miles, that net benefit is increasing, and then once we cross into amount of pollution greater than 25 units, and again, units here are river miles, we can see that the net benefit starts to decline. So again, this should illustrate to you that 25 river miles of pollution is the socially efficient outcome in the context of net benefits. We can see this also in a figure. So if we just were to graph these numbers, you can see that around 25 is where we get a plateauing of net benefit. And again, from a social perspective, we want to achieve the socially optimal amount of pollution, which would imply the socially optimal amount of pollution reduction as well. So because we've established here that 25 river miles of pollution is socially optimal, and again, because there is 50 miles of river currently being polluted, this would imply that the socially efficient level of pollution reduction would be 25 units. But we can actually take this a step further. So not only can we establish the socially efficient level of pollution, but if we have information about the firms in this particular industry, in this case the shipping industry, we can actually determine the most cost-effective level of abatement, that is pollution reduction, amongst both firms. So here what we're going to consider is that there are two shipping companies that operate boats on this river. And again, without any sort of environmental policy, we know that 50 miles of the river are going to be polluted. We also know from the first equimarginal principle that the socially efficient level of pollution is 25 units. This means we have an abatement goal. The goal of pollution reduction would be to reduce pollution by 25 river miles. So we want to allow pollution for 25 river miles. We want to abate pollution for the remaining 25 river miles. What we're going to use is what's called the second equimarginal principle, which says that the most cost-effective abatement policy will equate the marginal abatement costs across both firms. You'll notice, much like the first equimarginal principle, again, we're relying upon this marginal way of thinking. So in the previous example, we set marginal benefit equal to marginal damage. And now what we're going to do in this scenario is we're going to equate the marginal abatement costs across the two firms. Okay. So here we have the total abatement cost functions for the two firms, and here we have the marginal abatement cost functions for the two firms. Again, these marginal abatement cost functions come from the total abatement cost functions. They're simply the first derivatives of them. Again, you don't need to know that necessarily, but I think it does help to sort of see that everything here is very straightforward, right? We get our marginal functions from our total functions here, just like we did with respect to total benefit and total damage in the previous example. Now, what we're going to be able to do here is, by having the total abatement cost functions, we're going to be able to compare various abatement strategies and see which one is most cost effective. Here we will consider only two. The two that we will consider will be one in which the abatement goal of 25 units of river miles polluted to be abated, to be reduced. We'll assume that we just split those between the two firms. We'll see how much that costs. Then we'll use the second equimarginal principle to find what would be the theoretically most cost-effective approach and determine if it indeed is more cost-effective than simply splitting the abatement requirement across the two firms. So let's start with that example where we have a command and control policy. We have a command and control policy where each firm is responsible for half of the abatement strategy, which is 25 units. So both firms would be responsible to reduce pollution by 12.5 units each, and then of course that would imply that 25 units would be abated in total. So if firm 1 reduces their own pollution by 12.5 units, it costs them about $78 in total abatement costs. If firm 2 voluntarily reduces their abatement by 12.5 units, it costs them about $156. So in total, from this particular strategy of simply requiring both firms reduce 12.5 units of pollution, we can see that the total abatement cost is $234. Now, what we're going to do is we're going to use the second equimarginal principle to find the most cost-effective abatement strategy. So again, we take the marginal abatement cost for firm 1, we set it equal to the marginal abatement cost for firm 2, and that's this right here. Again, we can see marginal cost for firm 1 is just the abatement level for firm 1, and then the marginal abatement cost for firm 2 is 2 times their abatement level. This establishes for us an equation. Right? So we have one equation here that says that the abatement level for firm 1 will be equal to 2 times the abatement level for firm 2. Right? So this is an equation. Then what we can do is, because we know the total abatement goal is 25 units, we can create a second equation where the abatement for firm 1 plus the abatement for firm 2 is equal to the standard, is equal to the strategy. Okay, so now what we do is we have 2 equations and 2 unknowns, right? Anytime you have 2 equations and 2 unknowns, you are able to solve for each of the 2 unknowns. So that's what we'll do. So again, this is our first equation, which says that the abatement level for firm 1 is going to be equal to 2 times the abatement level for firm 2. So we just plug this into our standard equation. So our standard equation, again, is that the abatement for firm 1 plus the abatement for firm 2 needs to equal 25 units. That's the abatement goal. So we know that A1 is equal to 2A2. So we just plug in 2A2. You'll see that right here. So now we have this equation. It says 2A2 plus A2 is equal to 25. We just solve for A2. And what we're left with is that the optimal level of abatement for firm 2 is a little over 8 units of pollution abated. Here, this would imply that firm 2 is responsible for about 8 miles of clean river, or 8 miles of reduced pollution in the river. Okay. Notice we put a star here. This indicates that this is optimal. We have established the optimal abatement level for firm 2, and it's 8.33 units of pollution abated. Later on, we'll round these to make our life a little bit easier. Well, now that we've established that the optimal level of abatement for firm 2 is 8.33, and because we know that the optimal level of abatement for firm 1 is equal to 2A2, and again, we know this because when you set MAC1 equal to MAC2, the initial equation it found was that A1 is equal to 2A2. So, if A2 is 8.33, then this means that A1 is going to be 16.67, simply 2 times 8.33. So, in optimality, firm 2 should abate 8.33 units of pollution, and firm 1 should abate 16.67 units of pollution. Let's round these to make our life a little easier. We'll make this 8, and we'll make this 17. So now we see that the optimal level of pollution abatement for firm 1 is 17 units. Again, we just took 16.67 and rounded it, and the optimal level for firm 2 is 8. So now what we want to do is we want to calculate the total abatement cost and compare this to the command and control strategy that we saw previous. So if we take A1 equal to 17 and we plug it into their total abatement cost function, we see it's $144.50. Then if we take A2 star equal to 8, plug it into the total abatement cost function for firm 2, we can see that their abatement cost would be $64. When you add up the total abatement cost for firm 1 and the total abatement cost for firm 2, you get $208.50. Now recall that we established that if we simply split the abatement level evenly amongst the two firms, that the cost to do so would be $234. Now again, both of these scenarios abate the same number of polluted river miles, which is 25. So under this scenario, where we ignore the differences in marginal abatement costs, the cost to reduce pollution by 25 units would be $234. However, if we rely on the second equimarginal principle to establish the efficient amount of pollution reduction amongst the two firms, we can see, in fact, considerable savings, now with the total abatement cost only costing about $208. And this is the whole point of this process of both the first equimarginal principle, which establishes for us the socially efficient level of pollution, and also the second equimarginal principle, which establishes for us the most cost-effective way for us to, in a sense, divvy up the abatement requirements. Now the question becomes, how can we induce firms to abate at this particular level? And in the next video, the next lecture video, I will take you through several ways in which we could do that.